What's going on, guys? This video will mark the start of Chapter 5, where we'll be covering tree-based algorithms. So today we'll be covering regression trees, next section we'll be covering classification trees, and then after that we'll go into our ensemble methods such as random forest and boosted. Tree terminology. So first off, decision trees are non-parametric methods, so we're not going to estimate any parameters. They're highly flexible. They're easily interpretable. And they can be used for both regression and classification. So the cons is they often suffer from high variance. So our estimates usually aren't the most accurate. Now for the terminology. So over on the right, we're going to have a regression tree. It's a regression tree because we have numeric outputs, or our dependent variable is numeric. So the first split of our data is going to be known as the root node. And all subsequent splits are going to be known as internal nodes. So at each split, it's going to create two branches. Now at the very bottom of a regression tree, we're going to have our leaves. So in this regression tree, we're going to have three leaves. We're going to have 1, 2, 3, 4 branches, and we're going to have two nodes. The internal node, and then plus our root node. So now how do we use a regression tree? So a regression tree partitions our data with a couple set of rules. So every time we make a rule, we're going to have a split in our data. So here we're saying if x1 is less than 100, and then on one side is going to be if x1 is less than 100, and on the other side is going to be if x1 is greater than 100. Now if it's not given to you explicitly which side to choose for whether it's true or false, always assume that when this expression is true, we go to the left. So if x1 is less than 100, we're going to follow it to the left. If x1 is greater than 100, then we'll follow it to the right. And then if, say for instance, x1 is greater to 100, so we're going to end up at this node. Now we're going to get to another rule. If x2 is greater than 40, so if this is true, we're going to go to the left. If this is false, we'll go to the right. And then ultimately we're going to end up at our leaf node, and then this will be our final prediction. So if you're to enter an initial observation, say x1 is equal to 50 and x2 is equal to 60. So the first step we're going to take is from our first root node, which is x1 is less than 100. So since it is less than 100, we'll follow this to the left, and our final prediction would be predicted value is equal to 5. Now if we say our x1 is equal to 105 and our x2 value is equal to 50. So it's going to do our first root node is x1 less than 100. No. So we're going to go to the right. And we're going to get to our next node is x2 greater than 40. Yes. So we'll go to the left. So our final predicted value would be 7. And then our one more example, if x1 is equal to 105 and x2 is equal to 30. So our first check is x1 less than 100. Yes. Is x2 greater than 40? No. So we'll go to the right again. Our predicted value would be 8. So now we can draw out the predictions we'd get from our predictor space. So if x1 is less than 100, so let's say that's this whole range here, then our predicted value is going to be 5. Now if x1 is greater than 100 and x2 is greater than 40, so that's this whole range here, then our predicted value is going to be 7. And then finally, if x1 is greater than 100 and x2 is less than 40, or this whole range here, we would guess a predicted value of 8. So if we have any x1 value in this interval, we're going to guess a predicted value of 5. And then if we have an x1 in this interval and our x2 is less than 40, we'll guess 8. And then if it's greater than 40, we guess 7. Creating splits. So we just talked about how to make predictions from a regression tree. Well, now we're going to learn how to build our regression tree. So the way the regression tree is built is going to create splits that create the biggest decrease in the sum of squared errors. So first step, we're going to build our null model. So we're going to find the sum of squared error if we were to create no splits. So first step is to find our y-bar, so 50 plus 20 plus 60 plus 70 plus 50 over 5. And we'll get a y-bar equal to 50. Now we'll find our sum of squared error. So 50 minus 50 squared plus 20 minus 50 squared plus 60 minus 50 squared plus 70 minus 50 squared, and then finally 50 minus 50 squared. So we're going to get a sum of squared error for a null model equal to 1400. So the reason 50 was used is when we're using regression trees, we're going to take the mean of our observations in that individual branch or leaf, and that's going to be our predicted value. So that'll make more sense once we actually start building the trees. But for here, our y-bar is going to be equal to our predicted value. So that's why we're using 50. So our original sum of squared error is 1400. So now we're going to choose the split in our data that's going to create the biggest decrease in our sum of squared error. So in order to find our possible splits, we first have to arrange our predictors. So if we arrange them from increase in order, we can go from 3, 1, 2, 2, 4 to 1, 2, 2, 3, 4. And then just follow the y values. So 1 was paired with 20, and then 2 was paired with 60 and 70. 3 had a y value of 50, and then 4 had a y value of 50. So the possible splits are going to be the midpoints now between our x observations. So we can do a split at 1.5. So since there is no in-between between 2 and 2, that one's going to get skipped, so we can't do a split there. And then between 2 and 3, we do a split at 2.5. And then finally, we do a split at 3.5. So we'll start off with a split at 1.5. So we'll say when x is less than 1.5, and now we're going to create which way the observations will go. So since our first observation, x is equal to 1, is less than 1.5, it'll go to the left. So we'll have a y value of 20. Now for the other 4 observations, the x value is greater than 1.5, so they'll go to the right. So we'll have observations 60, 70, 50, and 50. So now the predicted values from this split would be, since there's only one observation, the mean is just going to be 20. And then for the right side, we're going to find the mean of these 4 values. So 60 plus 70 plus 50 plus 50 over 4. And we'll get 57.5. And since that's the mean of this side, it's also going to be our predicted value. So our predicted value is equal to 57.5. And on this side, our predicted value is equal to 20. Now we can find the sum of squared error for each side. So the sum of squared error for this side is easy. It's just going to be 20 minus 20 squared, which is equal to 0. And then for the right side, we're going to take our y values and then minus the value we predicted for them. So since the original observation was 60, and we predicted a value of 57.5, we would add an extra, say, 2.5 squared to our sum of squared error. And then we're going to add all these up. So the actual value was 70. We guessed 57.5 squared plus 50 minus 57.5 squared. And then finally, 50 minus 57.5 squared, and we'll get a sum of squared error equal to 275. So when we created this split, on the left side we just sum of squared error of 0, and on the right side we just sum of squared error equal to 275. So after the split, the total sum of squared error is going to be equal to 275. So we went from no split, 1400 sum of squared error. After the split, now our sum of squared error is going to be 275. So now we can do the same thing, but now we're going to try our second split, which is between 2 and 3. So we can say if x is less than 2.5, or the midpoint between the two, and now let's go about the same process. So the observations with x is less than 2.5 have y values of 20, 60, and 70. And then on our right side, if x is greater than 2.5, we're going to have 50 and 50. So we're going to find our y bar, which is going to be equal to 20 plus 60 plus 70 over 3, which is going to be equal to 50. So our predicted value, if it falls on the left side, is going to be equal to 50. And then on the right side, our mean is just going to be equal to 50, so our predicted value is going to be equal to 50. And if we find the sum of squared error on the left side, we're just going to take our observed minus predicted squared, so 20 minus 50 squared, plus 60 minus 50 squared, plus 70 minus 50 squared, and we'll get a sum of squared error equal to 1400. And then on the right side, our sum of squared error, we predicted 50 and both observations were 50, so our sum of squared error is going to be equal to 0. So our total sum of squared error after this split is going to be equal to 1400. So with the other split, our sum of squared error was only 275. So the first split, or x is less than 1.5, is now favored over x is less than 2.5, because we had a greater reduction in our sum of squared error. And then we have one possible split remaining, which is going to be between 3 and 4, or at 3.5. So if we build this split, if x is less than 3.5, so on the left we'd have observations 1, 2, 3, and 4. So 20, 60, 70, and 50. And on the right, we would have a sole observation of 5, which is just 50. So we're going to find the mean on the left, so 20 plus 60 plus 70 plus 50 over 4. So we'll get a y bar value equal to 50. And then on the right, our y bar is just going to be equal to 50, which is the same as our predicted value on both sides. So now we can find our sum of squared error, so observed minus predicted squared. So 20 minus 50 squared plus 60 minus 50 squared plus 70 minus 50 squared. And then finally 50 minus 50 squared. And this will produce a sum of squared error equal to 1400. And then on the left, our sum of squared error was just 0. So 1400 plus 0. So after the split, the sum of squared error we're going to have is 1400. So if we compare our three possible splits, we're going to have 1400, 1400, and 275. So from this, we can conclude that the best split for our data would be that x is less than 1.5. So our final model for using only one split would be that x is less than 1.5. Now, if we wanted to continue this, we could, where ultimately we said x is less than 1.5, and on the right, we're going to have 4 observations. So from these 4 observations now, we could perform another split. And on the left, we only have 1 observation, so that, of course, is our final leaf. We can't go any further than that. Early stopping and cost complexity pruning. So one problem that can arise from decision trees is overfitting, where ultimately you just keep splitting your data into smaller partitions in the hopes of lowering your sum of squared error. So one way to account for this is with early stopping. So with early stopping, we can say, don't make a split if the number of observations in your leaf node is less than 5. Or don't make a split if the decrease in your sum of squared error is, say, less than 100. Now the problem with this is that sometimes a bad split, where say the sum of squared error decreases by 5 or 10, can lead to a good split, where the sum of squared error then decreases by hundreds, if not thousands. Now this is caused because decision trees use a greedy approach. So what this means is that the decision tree will make its splits from the top down, and when it makes a split, it won't consider future splits. So this will be a first split, and it will choose whichever observations creates the biggest sum of squared error decrease at that moment. It won't then consider this one until it gets to it, and then it will choose whichever one creates the biggest decrease in the sum of squared error. So ultimately, it might not choose the best splits that create the lowest sum of squared error overall. It'll only create the best splits at that moment. So one way to account for this is to use cost complexity pruning. So with cost complexity pruning, we're going to build a large tree and then start shaving it from the bottom up. So the advantages of this, if a bad split then leads to a good split, we'll be able to account for this. So the formula we're going to use is the sum of squared error of our tree after the splits, plus, and then the number of leaves that it has, and then times our tuning parameter, alpha. And then we're going to choose whichever value creates the smallest one from this formula. So this is essentially going to be our penalty that's added for having too many leaves. So here's our regression tree that's fully grown. So from this regression tree, we're going to have three possibilities. We're either going to have the full tree, or we can cut this node, or we can just use our intercept. So if we were to cut at this node, this is what our tree is going to look like. And we're going to have a sum of squared error equal to 0, and a sum of squared error equal to 275. And if we were to just use our intercept, we have our sum of squared error equal to 1400. So our possible options is we're going to have our full tree, which has 3 leaves, and a sum of squared error equal to 50. So our formula is going to be our sum of squared error plus our number of leaves, and then times our tuning parameter alpha, which here we're saying is 300. So this is going to be our full tree. Now our second option, which is going to be one split, and we're going to have a sum of squared error equal to 275 plus 0, which is just 275, and it's going to have 2 leaves. So with one split, we're going to have 275 plus our 2 leaves times 300. And then finally, we are going to have no splits, or just our intercept, and the sum of squared error is going to be equal to 1400. And then the number of leaves, which is just 0. So after we add our tuning parameter, values we're going to get is 950, 875, and 1400. So you want to choose whichever one creates the smallest value. So from this, we can see that with a tuning parameter of alpha is equal to 300, the best model we can choose is going to be our one split for with a penalized sum of squared error equal to 875. So our final regression tree would just be our one split. And then the way you would choose alpha is ultimately you could just choose different alpha values and you'd use cross-validation just like you would with any tuning parameter. The alpha tuning parameter though, unlike lasso regression, where if we adjusted our lambda ever so slightly, we'd expect different coefficient estimates. But with alpha, we can adjust our alpha value and we're still going to end up with the exact same model. And in the range of our alpha value, we can find out where our model stays exactly the same. We can just solve with an inequality. So here we're going to use 50 plus 3a, which is just our equation for our full tree. And we want this to still be greater than our value of one split, or 275 plus 2a. And then if we were to solve for this, we would get 225 is greater than a. So our a value has to be greater than 225. And then if we were to solve for another inequality, which is no splits, so we would say that 1400 has to be greater than 275 plus 2 times a. So we would say 1125 is greater than 2a. So a is less than 562.5. So finally, we can say that a is between 562.5 and 225. So any value we pick for a in this range, we would get our exact same model as the one we got for when alpha is equal to 300, which is just going to be our decision tree with our one split. And we're going to get the exact same predictions. So when you're choosing your alpha value, you have to take into consideration what scale your y or dependent variable is on. Like, for instance, if your y value was 0.01, 0.02, you need to choose a very small alpha value compared to if they were in the tens of thousands, where your sum of squared error is expected to be much higher. Transformations. So any transformations you apply to your independent variable will not affect your model. So for instance, even if we take the log of our independent variable, which observations 1, 2, 3, we would then get values 0, 0.69, and 1.09. So if we were still using our original y with our ln of x, we would still make the exact same splits. So is it between 0.69 and 0, then we'd have 30 on the left. Is it between 1.09 and 0.69, then we'd have 10 and 30 on the left and 25 on the right. And that'd be the same if we applied no transformation. So it would make the exact same split, so any transformation you apply to your independent variable won't affect your model. But now if you applied, say, the log of your dependent variable, it will affect your model. So if we were to apply no transformation and we were to make a split between 1 and 2, so we would have 30 on the left and we'd have 10 and 25 on the right. So our predicted values would be 30 and 17.5. So now we're going to apply our log transformation to our y. So we're going to have values 3.4, 2.3, and 3.2. So if we make the same split, we're going to have 3.4 on the left, and then 2.3 on the right with 3.2. So we're going to find the mean on the right. We would get a value of 2.75. And then on the right, our predicted value would be 3.4. So now if we wanted to transform this back to our original units, we could say the exponent of 3.4, which is going to be equal to 30. So this was our original predicted value, so it did well there. But then on the right, if we were to find the exponent of 2.75, our predicted value is going to be equal to 15.64, which is not equal to, if we weren't applied to the transformation to our dependent variable, of 17.5. So transformations affect your dependent variable. It affects the outcome if applied to your dependent variable, but doesn't affect the outcome if applied to your independent variables. And then finally, how do we use categorical predictors? So you don't have to create dummy variables like you would for linear regression with decision trees. And that's another great thing about decision trees, is that they're so easy to use because you don't have to do really any data pre-process it. So if we want to make a split based off the color, we're ultimately have three choices: red, white, and blue. So our possible splits are going to be, is color equal to red? Is color equal to blue? Or is color equal to white? So let's say we want to make a split of color equal to red. So that means on the left side, we're going to have our 20 and our 55. And then on the right side, we have our other three observations, which is going to be 40, 30, and 70. And then you would solve for it just like you would any other way, which is just you're going to find your mean, and that's going to be your predicted value, and then you're going to find the sum of squared error based off that. And whichever one of these colors produces the lowest sum of squared error, you'll choose as your split. So that's going to wrap up this section on regression trees. Next section, we're going to learn classification trees. So a lot of this is just going to repeat itself. It's just the only thing that's going to change is how we choose which one we make our splits, because it's no longer going to be based off sum of squared error. So I hope you enjoyed, and I'll see you next time. Thanks.